I mean, I'll tell you, like you see, you would have studied topology, you've studied, forget topology, you've studied metric spaces, or you've studied R2 analysis on R2, right? And you've studied group theory, right? Sometimes what happens is you see there are some surprising results come in analysis, right? And sometimes what happens is those surprising results are coming because of this mixture of two very different kinds of things, which is algebra and analysis. Okay, I'll give you an example. So a topological group is something which I described. So topological, I mean, I'm just using some words, but you have concrete definitions and examples. And when you try to prove that they are topological groups, then that's basically your exercise. Yeah. So I would just say that you can do one more example, which is the same, but try to do this. Show that M and R is a topological group. Okay, this is not a big deal. So even the norm thing that I asked you to do, if you try to check those things, I mean, that's how you actually mix the concepts that you've studied. Otherwise, people just sit and revise the concepts. That's no good, I think. Yeah. But yeah, let me show you one feature of topological groups. And this is where you see all the work will come. So let G be a, so this is, I mean, not related to Cauchy sequences, but I'll just do this quickly. So this be a topological group. Yeah. So you people, two questions. Do you know what is a T1 space?
No.
No? Okay. So this is a space in which points are closed. Very important space. Important class of spaces. All the spaces you have is where basically points are closed. So what will happen in an exam? They'll basically not say this. They'll say that X is a topological space where points are closed, right? That's maybe how it's say. Okay. So T1 is a space. T1, I say T1, it just means that points are closed. All the points are closed. Okay. And Hausdorff, you know, do we know what is Hausdorff? Can anybody define what is Hausdorff? No, you don't know what is Hausdorff?
No.
Oh. Vaishnavi, can you define, do you know Hausdorff? Can you define Hausdorff?
No, no.
No? Okay, you studied at some point, I suppose, but okay. So Hausdorff means that given 2 points, given 2 points, x and y, there exists u, x, u, y, containing x and y. Yeah, x and y.
It can be separated.
Exactly, yeah, such that ux and uy are disjoint. Right, so you should read these things, right? So okay, so then maybe I will not do the exam. If you have never seen these two, what these two things are, then it's, yeah. So I mean, I will suggest that you read Moncrief's points at topology. Points at topology is like the step theory that you need to do mathematics. Otherwise, you cannot do any serious mathematics. I mean, at least one side of maths will be completely inaccessible without doing. Okay, sorry. Points at topology. There is a book. It's just, I think it's just called Topology. But you should see there are some basic definitions, and you should read and try to understand the differences and similarities. So okay. Then I would want to say more, but maybe I will not say. Okay. But I will. Okay, that also I should not give if you have never seen what that is. Okay. All right. Then we have some exercises there. in those concepts. So tell me then, what do you guys want to know about Cauchy sequences? You know the definition. So what is it that you want to know about Cauchy sequences? Anything in particular?
Like,
Any questions? Otherwise, I'll say
no,
something general. Yeah.
no, not anything
Not anything
particular.
specific. Okay. All right. So basically, then yeah, let's specialize to metric spaces. Let's then maybe because if I'm in topological spaces and I want to say it's a bit problematic. Yeah, if you're not comfortable with Hausdorff and T1, then we'll say metric spaces. We obviously all metric spaces are Hausdorff and T1 and so on. Okay, they are everything, not everything. Yeah. So there is one of the nice things about Cauchy sequences, right? So number one is that Cauchy sequences are bounded, right? Do we know this? They are very important,
Yes.
right? Yeah. So let's not prove it. I mean, this is easy. And the second property, which is a Cauchy sequence is convergent if it has a convergent subsequence. Right? Is this something which you know? You can feel this? Think, take time and think. The definition. Yeah, is this correct? Do you know? Try to see one direction. I mean, if it has a basically the only one direction is interesting. It has a convergent subsequence implies that the whole thing is convergent. That's the good thing, right, about Cauchy sequences. So obviously you are assuming it is Cauchy and then you're proving this. So there is so if I want to write it, I suppose you can do all this, but I'm still, yeah, just do it on pen and paper and see. It's correct.
I think the converse is not true.
Right? Why?
I've studied somewhere. I can't remember.
Oh, okay. So it's only from memory. All right. But try to see, I mean, try to also
Yeah.
see if it sounds good, if it feels correct. You have to
I'm
use all
just
the
I
anchor.
can just tell you the subsequences if they are only converging, but that doesn't mean the whole sequence will converge. Kind of
Cauchy
that.
condition. No, Cauchy condition is there. I know that. But under the Cauchy condition, I am asking this question, right? Otherwise, I know. I mean, that is trivial. I understand. Yeah. Hmm. Yeah, this is something that you should know. I mean, so when you prove that in R the Cauchy sequence is convergent, how do you prove it? You show that there is a convergence of sequence, and then you show that the sequence is convergent. No, the intuition is, yeah, this is something that you, if you've read the proof of Cauchy sequences are convergent in R, then you cannot, then you should know it. Now the point is this: there are Cauchy sequence, right? The point is that, I mean, look, the point is that if a Cauchy sequence does not converge, it's because it's because your space doesn't have enough points. That kind of matter, right? So if you have some subsequence, some subsequence which converges, right? Then because so they go to some fixed point, kind of, right? Then the other points are pulled towards it. No, the other points are pulled towards it because of the Cauchy condition, right? So it is true. If you have one limit point, then that's the only limit point and everything goes to that point, right? So please prove this for homework, or read. I mean, if you read Cauchy sequences also, but proving it yourself is really what is important. Yeah, because how much mathematics the internet knows or the book knows is good, but how much mathematics you can generate is what is is what matters in the exams, or especially more in the future. Right? Even in exams, how much mathematics you can do in that 2 hours is what counts. So please, I mean, I've given you the intuition. It's not like please try to prove. I want to get to more interest. We see Cauchy sequences share an interesting property with something called an ultranet. Okay, ultranet. So these are very interesting objects, ultranets, and uh, yeah, I suppose, yeah, ultranets, or you can also say ultrafilters. They're kind of similar concepts. Okay, yeah, probably I cannot say this right now, but what is being said here is that if the sequence is if the sequence is infinitely often uh, yeah, of course, both the directions are true. No, the converse is not true in general, but if we need Cauchy sequence, then it is true. Okay, we need Cauchy sequence, then it is true. Yeah. Okay, anyways, I'll move forward. I mean, alternates, I would try to say that if we would have done more of the Bolzano-Weierstrass, means not that, but monotonic subsequence business. But anyways, we'll move forward. Anything more interesting about Cauchy sequences? Yeah. So obviously there is a very important definition. There's a very important definition. What is it? Complete, right? Yeah. A complete, if, I'm just writing if because this is a definition, if all Cauchy sequences converge. Right? You would want to make your Cauchy sequences converge. If all the Cauchy sequences converge in your space, and the space is called complete. Right? Also called Cauchy complete. Correct? This is an important side of Cauchy sequences. What else is interesting about Cauchy sequences? So please, you should read about these complete spaces. There are many properties like closed subspace of complete space is complete, and so on and so on. right? Basically, but then let us then look at the following. Let's look at the following, and I don't know the proof of this, so we'll have to look at it, look at some reference. But this is really the result. Okay, so x comma d be a metric space. Okay, then there exists a space x prime, okay, such that or maybe I should say that there exists a space x prime with a metric d prime, correct? So what I'm trying to say is that if you have any space, right, then you can put it inside a complete space. You can add some points and make the space complete. You see what I'm saying? This is the topic, right? This is a topic of Cauchy completion. Obviously, I will not be able to cover the whole topic, but I would like to give you the ideas so that you can. I mean, if you read Cauchy sequences, that this is what you should read after this, right? So Cauchy completion of a metric space. And then you can also think of this in the case of R, that Q can be completed to R. Okay, that's a special case of this. So if you look at the Cauchy completion of a metric space, then what I am saying is that there exists this space x comma d bar d this thing, okay, such that just think of it like x is a subspace. Okay, x is a subspace. Okay, x is a subspace. I mean, such that yeah, let's just think of yeah, as subspace. So what I'm saying is that this is true, that d of x comma y is equal to d prime of x comma y. So d and d prime agree on x. Obviously, d prime has more elements, so more things have to be thought of, and so on and so on. But yeah, okay. But on x, d prime and d are same. Okay, this is what I'm saying. Right? So I'm thinking of x as a subset of x prime. So this happens, and then this. So you can completely think of x as a subspace of x prime with the same metric. Yeah. Such that the closure of x is x prime. So you can keep in mind q and r. You know that q is dense in r. You know that distance between 2 points in q, if you view them in q or if you view them in r, the distance doesn't change. So it's like that. Okay. And x prime is complete, and you know r is complete. Yeah. So for any metric space, there is always this completion, the smallest metric space which you can, smallest way to extend x prime so that you end up in a complete space. I mean, you can also think of this as x is dense in x prime. Right? Every point of x prime is a limit point of x. Correct? So why can this be done for any metric space is really a important question, fundamental question. We always say, okay, the metric space is not complete, or you complete it. And consider its Cauchy completion everywhere. Sometimes it preserves what you want to prove for x, sometimes it destroys what you want to prove for x. So, you know, it's right. But why can this be done? That is the question. Again, if X was a topological group, then it would be easy. I mean, then one can use algebra because you have group structure, maximal ideals, and so on. But yeah, in general, that is not there. So yeah, let's see. I mean, one can think, but you see, this is a question. So let's. So this is a theorem. I mean, this theorem is a theorem. You cannot just think of it on your own, maybe. But it's a very important theorem. Yeah. Let me see the proof. It's proof. The proof is not there, but it's there through a sequence of exercises. So let's see. Try to absorb the statement. Okay, actually it's a theorem, so nice, good. So they actually prove it. Just a minute. Right. So it's interesting. It's interesting. I'll give you the reference, but first let me talk about the proof a little bit. Yeah, it's very interesting. So you consider the space X, and then you consider this space. Okay. So see, I'm telling you some abstract constructions, but when you fill in the gaps, is where the exercises are. Okay. If to show something is closed, something is continuous. This. What is this? This is the collection of all bounded collection of all. No need to write all, right? Collection of bounded. Yeah, actually I should write all bounded functions, right? From X to R, right? Let me just check. Right. Okay, okay. So first of all, you have to know why this is true, right? So I mean, first of all, if you come to this, then there are some exercises. Otherwise, it's difficult to move forward. So yeah. So if you look at this space, right? This is just a set, right? If we want to make it a space, now how do you make it a space? Right? You put a metric on it, and as books notice, I am also denoting it by row. Okay. And what is this? This is a metric. What is a metric? Row of f comma g. So these are bounded functions, right? Bounded functions from X to R. X is a metric space. It's everything is met. It's not a topological thing because it's Cauchy. So what should this be? Well, this, as you can imagine, the bounded condition is there to is a supremum of fx minus gx, right? x. You would have seen this metric, right? Sequence of functions, if you have done, this metric comes up, right? Okay, this metric. So, I mean, you should show that this, maybe I'll call my x prime, that x prime is complete. Okay, this is also a standard problem in sequence of functions chapter, right? Even if you take continuous functions, that also is complete, right? You know that your uniform sequence of continuous functions gives you the limit is continuous, right? But anyways, I mean, if you forget that for a moment, you can just prove this from scratch, that this space is continuous. This space is complete. Maybe that is what we should do right now. I think it's better than proving that this completion can be done, right? Right? I think that's a better exercise, right? So yeah, let's just do that exercise. So we will do this thing next time. But this that BXR is really the key. Okay? These techniques are very useful. Okay? So how do you show that this is complete, that this space is complete? So how do you do that? You see, this is basically based on the fact that R is complete. You have to use the fact that R is complete, right? So yeah. So let's see. Let's take a Cauchy sequence. Yeah, P Cauchy in BXR. I've told you the sort of the key point here that R is complete. That is why things you build on R are complete. Something like that. Right? So this is a Cauchy sequence. So what does it mean? I mean, it just means that so you've given an epsilon, and then you know that fnx minus g minus fmx, right? Just the definition I'm using, okay? Is less than epsilon for all x. This is just in this metric, I'm expanding the definition, right? Sup I'm also removing by this, correct? For all n and m bigger than equal to n naught, right? But well, your goal is to find limit. What is that limit going to be? What is my limit f? How will I construct the function f? Is this clear? This Cauchy translating to this? Like this is, I'm just writing like this. This is what I should write, but this translates to this for all x also, because there was a sup there. The supremum of something is less than, it means for all x it is this, right? Okay. But where is my function f? Well, I can just find it, right? Because if you forget this x for all x, then you know that for every x this is true. So now you have a Cauchy sequence in R. Correct. So then you know that f1, f1x, that's a Cauchy sequence in R, right? That's how you use the thing. This is a Cauchy sequence in R. This sequence, you know that it converges to something, right? Because R is complete. So I'll call it fx. Because that's, yeah. So my f is constructed. Right? So my f is constructed in this way, yeah. So f is constructed. What do I have to show now? We have to show that this f1, f2, and so on, they converge to f in that row metric. That you need to do for homework. Because so far we have not proved that. We have just proved that for every point, this converges to fx. Right? And that doesn't imply immediately, but it will imply if you just think about it for some time. Okay. Is it fine? So this is a nice exercise. Okay, you have to show that this thing is working. Okay. So maybe this is where I will stop, right? But if you are if you're interested, then you should. I mean, this is just a. I'm just saying. I would like to say this properly next time. But because now you know that this space is compact. Sorry, this space is this space is complete, right? So you want to push the. You want to. This is what you want to do, right? You want to push your x. So just see it on an overview level, not in a detailed way. Otherwise, you'll get confused at the moment. That you have to work out. But this x, you want to push this x into a space which is complete, right? Just think about that, and then everything else will work out. This is complete, you know already, right? How do you push x into A? So given a point of x, how do you take it to a function? You have to take it to a function. What function will that be? So that function they are suggesting is you fix a point x naught for all, once and for all, okay? And then given this A, you need a function from x to r. So based on this A, you need a function. So what will that function do? So this is A. Now we need a function. So what will that function do? R. So what will that function do? It will take any point x and it will return this distance minus this distance. That's the function. So every point is going to a function. This is the idea, right? This is the idea. This is the function I want it to go to. Okay, every point goes to a function. Now what do we have to check? We may have to check many things, but you can check everything, all of them. You have to first list out what you have to check, and then you can check them. Obviously, you need to check that this is bounded because you want to say that the output is in this space. So you show that it is bounded. Then you have to show that it is 1, 1, right? You have to show that it is 1, 1, and then you have to show that it preserves the metric, right? That your d of a comma b is equal to rho of phi a comma rho of phi b because it's going there, right? You're sending it there, and there it has to be same, right? This point is a bit different from how I said. I said it's subspace, but that method is not. That is not a good approach, I would say. It's the same thing, but it is confusing. Then what will happen is you will just show that this phi x, right, is inside this space, right? And this is same as x in the sense that everything is same. A is getting replaced by phi a, but everything else is same. The metric is same, points are same. So 1, 1 function, and the metric also matches. Metric symbol is different. Element ka symbol has changed to phi. It has become a function, but it's actually acting as the same thing, right? Okay. Then you have to say that this image is this is a closed subset. You have to say that this is a closed subset in this space, right? And closed subset. No, sorry. It's not closed. Why should it be closed? It is not closed. Yeah. You take phi x in this space. Now, what is your Cauchy completion? This is not your Cauchy completion. This is just a complete metric space. Big, I don't know how big complete metric space containing phi x. How will you take? Just take the closure now in this space. When you are in a complete space, in a grandmother complete space, then if you have a subset phi x, you can just take its closure. And this is a closed subset of a complete space, so it will be complete. And then you say dense. Now this is dense in this, right? It's a very nice idea. It's a very nice idea, right? Yeah. So this point x naught is not important, but in the case of a topological group, yeah, but how is this function motivated? That is very interesting. I don't know. You see that this is really the main thing is this function. Okay? So given x naught is fixed forever, you can take it to be 0 if your space has a 0. And then there is a, and then you are sending it to this difference. correct? Yeah, because at A it will give you this will become 0. Yeah, probably one has to think about it. Maybe while checking injectivity it will come into play. Okay, but anyways, these are the things. Yeah, but then you can just read this. But yeah, it's a lot of work if you want to read this chapter. Complete metric spaces. Complete metric spaces of function. But at least the first section you can read. A second section onward actually becomes complicated. I mean, it becomes a different game. This is just the first section. Space filling curve and so on. But yeah, over time you will understand everything. Okay. Yeah. So yeah, that's fine. Yeah. So maybe we'll meet next. When are we meeting next? Are we meeting tomorrow? Or then are we meeting on Saturday?
On Saturday.
Right. So let's meet on Saturday. So we are meeting on Saturday morning with.
I won't be available for this week.
Oh, you'll not be available for this week at all. All right. All right. No
No.
problem. Yeah. Okay. So then, Vaishnavi, then what are we doing on Saturday? You're going to present something, or you think? And let me know anything. I mean, anything. It's fine. Okay.
Okay.
Right. Yeah. You decide, because I have laid a lot of the things have been laid on the table, but you should plan and do so that, yeah. So then Saturday morning we'll meet. Okay. 8:30. 8:30, right?
Okay. Yeah.
Okay. Then that is done. All right. Okay. Okay. Bye.